Yeah, recording has started. Welcome, everyone, to the what you call the Gate Study Group, and I will hand over to Nikhil to handle. And Jamie, you are the starting one, right? So you start with your this one. I have put it on recording, and let me make you Jamie co-host, right? Are you everybody co-host or what? Uh,
Not sure about the
let,
co-host thing.
let
I'm
me
not the co-host.
just a second. Participant. So let me. Yeah, Nikhil Murray is also co-host. So Nikhil Murray is co-host. So let him handle. I have put it on recording. Go ahead. Thanks. Jamie, start with you.
Yeah. Shall I start or Nikhil? Is there anything you want to say?
The other way is I can make you co-host, and then once you change, you make Nikhil co-host. Okay?
Yeah.
Yeah. Go ahead. Thank you.
Okay. Thank you. So hello. This is the session regarding the gates preparation, and today I'll be covering some of the topics from the probability distributions. So we'll first start with uh, no, just basic concepts regarding the probability, and then we'll move further with its type for discrete and continuous variables. So, uh, starting with just a second. Okay. So, probability distributions are divided into two parts, mainly discrete and continuous random variables. Discrete meaning uh, they have their individual values and countable ones, and that we are trying to predict. And those discrete random variables are further divided into probability mass function and cumulative distribution function. So probability mass function, they take a particular value, whereas in cumulative distribution function, they take values up to a certain value. So you can imagine it as a in a range or up to a certain range. A similar kind of thing happens in the continuous random variables, where we try to predict the continuous values for the random variables. And those are divided into probability density function and a cumulative distribution function. So in probability density function, it the values happen in a small neighborhood of x, whereas in cumulative distribution function, it is similar to the ones that is happening in the that was discussed for the discrete random variables, where uh, a value is taken up to less than or equal to a value of k. So discrete random variables is as discussed here, they are described using the probability mass function and cumulative distribution function. So you can see for the example that probability mass function for a number of fraudulent transactions at an e-commerce platform is 10. So it will be written as a p of x equals to 10. Whereas for a cumulative distribution function, it takes a kind of a range or a value less than or equal to 10. The other examples of it are credit card rating, number of orders received, then customer churn, and fraudulent transactions. So for probability mass function, taking a simple example of heads and tails, if we toss the coin thrice, which are the combinations that are available? So all of them, all of the outputs are present in the sample space, and we want to know number of ways heads can be in the result of those three tosses. So we have the random variable x equals to 0, 1, 2, and 3, where number of ways head can be the part of it. One for x equals to 0, where head is not present at all. For x equals to 1, head appears once, x equals to 2, head appears uh, twice, and x equals to 3, head appears once again. So out of those 8 possible values, the probabilities are 1 by 8, 3 by 8, 3 by 8, and 1 by 8 for the values of 0, 1, 2, and 3. Now, regarding the cumulative distribution function, let's say we are rolling a dice and we are interested in the probability that the outcome is less than or equal to 3. So for that, we roll a dice, and what is the probability of getting 1, 2, and 3? So you can see that for as we are interested in getting the probability of having equal to 3, so we have 1 by 6, 2 by 6, and up to 3. So it's 3 by 6. So the CDF gives you the cumulative probability up to a certain value, and adding all the probabilities for getting values less than or equal to that specific value. Because we were interested in getting equal to 3, we uh, took into consideration the values that the probabilities of value getting equal to or less than 3. Now we were talking about discrete variables, but now we will be talking about the continuous random variables. So the continuous random variables are described using the probability density function and cumulative distribution function. Similar to the discrete random variables, the cumulative distribution function again will take a value less than or equal to a certain value, whereas in probability density function, it will take a value in a small neighborhood of x. So you can see that a probability density function is defined mathematically as f of x equals to limit delta x tends to 0, where the value of p, value of uh, sorry, probability lies, probability of random variable x lies between the value of x and x plus delta x. The other normal day-to-day life examples for continuous random variables are market share of a company, then it can be anywhere between 0 to 100, then a percentage of attrition of employees of an organization's attrition rate for employees, then time to failure for an engineering system, then time taken to complete an order placed at a e-commerce portal. These are all continuous values. Now, probability density function. So, for its example, we are taking the height of people from a population. So, probability density function tells you the relative likelihood of a random variable falling within a specific range of values. So, considering the heights of adults in a certain population, if PDF tells you that the probability density function at a height of 170 centimeter is 0.02, it will mean that the likelihood of randomly selecting an individual with a height very close to 170 centimeter from this population is 0.02 per unit of height. Next is a cumulative distribution function. It will take up a range. So uh, less than or equal to a certain value in a way. So again, we'll be taking the value of examples of heights, and you can see the given heights are 160, 165, all to, till 190, and the number of individuals with height less than or equal to 170 is 3. So the total number of individual is 7. Just a second. Yeah, so if for f of 170, uh, if we take it, it's there are uh, three total people out of 7. So the probability is 3 by 7. So in general, the f of x is given by probability of x being smaller than x, where capital X is belonging to representing the random variable, whereas x is the specific value. So, cumulative distribution function for discrete and continuous. For discrete random variables, the cumulative distribution function is evaluated at each possible value of the random variable, whereas for continuous values, they can be evaluated at any point within the range of possible values of a random variable. So this is the difference between the cumulative distribution function and of discrete and continuous random variables. Now, starting with just a second. Yeah. So before we start with the probabilities, there are some addition rules of the probability, where you can see that probability of any two events A and B denoted by A union B is equals to probability of A plus B minus probability of A intersection B. If they are mutually exclusive, meaning that they cannot occur together, then probability of A union B is only equal to probability of A plus B. And the complement rule, which is probability of A not happening, is denoted by A dash. So that's a complement of A. So probability of A complement is equals to 1 minus probability of A. And then the addition rules for 3 events, which are A, B, and C, is given by the individual summation of probability A, B, and C, then minus the intersection of AB, AC, and BC, plus the intersection of A, B, and C. So our first probability distribution is a binomial distribution. So a random variable x is said to follow a binomial distribution. So binomial distribution is basically having two probabilities, failure or success. So that's why binomial. So there. So the objective is to find the probability of getting X successes out of N trials, which are also called as Bernoulli's trials, and the probability of success is P, and thus the probability of failure is 1 minus P. And the probability does not change between trials, it remains constant. So a customer's churn, then fraudulent insurance claims, and loan repayment for default and no default. These are all the examples of binomial distribution. So when we use formula wise, binomial distribution is written as in combination with uh, combinations formula. So ncx into a raised to x, b raised to n minus x, from where the probability of success is denoted by a, the probability of failure is denoted by b, and a number of trials as well as the random variables for the success. Just a second. Yeah. So this is the formula that we just discussed over here, which is appearing at the very last, which is NCR1. But uh, if we uh, substitute the formula for the combinations, which is n factorial divided by r factorial into n minus r whole factorial. This is what the whole simplified formula would look like for the binomial probability distribution. And you can see the substituted expressions over here as well as the meaning of them. So for so taking an example for the binomial distribution, calculate the probability of getting 8 tails if a coin is tossed 10 times. So first, number of trials is 10 because we are tossing it 10 times. Then number of successes that we want, or what we want is 8 tails, is 8. So the probability of a single trial is 0.5 out of the two outcomes. One is tail, so 0.5. And and because we are going to use the formula, so we'll be using the combinations. We'll be calculating the combination for NCR for our values. So substituting the values for n equals to 10 and number of successes, which are r, is 8. Substituting the value and calculating it, we get 45. Now p raised to r is equals to 0.5 into 8, which comes to around 0.003 or 39. And substituting those values calculated into formula for NCR, it's 45. PR is p raised to r is 0.0039, and 1 minus p whole raised to n minus r is and multiplying them, we get, sorry, yeah. So the product of these two is 0.175 and 0.5 whole raised to 0.5 square being multiplied is a 0.043. So the probability of getting 8 tears is 0.04339. So these were the same values of formulas that were used for the uh, binomial distribution. Now moving forward to Poisson distribution. Now Poisson distribution is as a binomial distribution was used for uh, binary probability calculation of probabilities like success and failure. Poisson distribution is used when we want to know the probability of an event occurring at a fixed time of an interval. And these events occur with a known constant mean rate, which is and independent of the time since the last event. So these are independent events, and the Poisson distribution is for value k is given by e raised to minus lambda, where lambda is the rate of occurrence of the event into lambda raised to k by k factorial. The examples for the Poisson distribution are a number of printing mistakes per page, dishonored checks at a bank, then cancellation of orders, customer complaints, typographical error in the book, then number of potholes on roads, and etc. So for Poisson distribution, as we discussed the the formula, this is given in a different form, where instead of k, it's used as x. But let's just uh, look at look through one example. So example one, a random variable x has a Poisson distribution with parameter lambda such that p of x equals to 1 is zero point 0.2 and p of x equals to into p of x equals to 2. So we want to find p of x equals to 0. So first, uh, using the formula and substituting the formula for p equals to uh, 1 and calculating the value of lambda, we get lambda equals to 10. And substituting the value of lambda equals to 10 in the formula for p of x equals to 0, we get e raised to minus 10, which equates to the value of 0.0000454. The next distribution is exponential distribution, which is used for until a certain specific event occurs. Like in the Poisson distribution, we discussed about an event occurring at a constant rate. In an exponential distribution, we wait for a specific event to occur. Like an earthquake is a most common example when we talk about the exponential distribution. That if an earthquake has occurred in the past, till how much time that it will occur again. So traditionally used for time to failure of an electronic component, the exponential distribution represents a process in which events occur continuously and independently at a constant average rate. So as the examples are an event of an earthquake or long distance business telephone calls. or how much a car's battery lasts. So exponential distribution is used when we want to check reliability for something. So the PMF or just a second. So exponential distribution is given by f of x equals to lambda e raised to minus lambda x, where the value of x is greater than 0. And lambda again here represents the rate of occurrence of an event, where in exponential distribution, the of mean is equal to 1 by lambda. So uh, the exponential distribution is a continuous probability distribution that often occurs at the amount of time until some specific event happens. So you can see the formula for it. F of x for an event x is given by x given lambda. For values of x being x capital than 0 is given by lambda e raised to minus lambda x, and 0 for x uh, if x is smaller than 0. So discussing example for the exponential distribution problem, that you usually have two phone calls per hour. Calculate the probability that the phone call will come within next hour. So given that two phone calls per hour is there, uh, we would expect that one phone call at every half an hour. So we can take lambda value equals to 0.5, and substituting those values in the formula that we discussed of lambda e raised to lambda minus lambda x, and calculating the value, we get the value of 0.393. So the probability of arriving the phone call within the next hour is 0.393. Now the last distribution is a normal distribution, which is also known as Gaussian distribution. So a normal distribution is used to observe many naturally occurring events, and it's measured. So so whenever we use the normal distribution, it uh, forms this bell-shaped curve, and you can see that uh, how the normal distribution is work. The mean it's mean the average is at the middle of it, and according to the standard deviations, it will capture the data. So for plus minus one standard deviation from the mean, it will capture 34, and total 68% of the data. If we increase the standard deviation by one, plus minus two standard deviations, it will almost it will cover 95% of the data. And if we again increase it by one, then it will cover 99.7% of data. And there is no range specific for a normal distribution. So it can start from minus infinity to plus infinity. But the coverage of data, you can approximate using this. You can count using this, not approximate, count using this. So, no, a normal distribution, also known as a Gaussian distribution, is given by uh, f of by a function with x mean and standard deviation sigma is 1 by sigma into square root of 2 pi into e raised to minus x minus mu whole square, and in the same power in the denominator 2 sigma square. And the notations are the same. X is the variable, mu is the mean, and sigma is the standard deviation. You can see the other kind of graph regarding that, uh, and another representation that the average lies in uh, the curve is split using the mean, and according to the standard deviations, it covers the different range of the data. So this is a Z value table for. Let's calculate the normal distribution simple using a simple example. So we have the value of uh, x equals to 3, average is 4, and standard deviation of 2. Just simply substituting those values in the formula that we just saw for the normal distribution, and calculating the value of it, we get the value of f of 342 uh, equals to 1.106. So yeah, this was it for the normal distributions, and yeah, I'll be going back to Nikhil Moore.
Yes. So I'll start with the digital circuits section in which I'm planning to tackle the most of the uh, digital logic binary operations. So am I sharing my screen? No.
No.
Yeah. So I think the slideshow is ready. Uh, so basically, it starts with some fundamentals about what digital signals are and why is it called binary. Uh, it just means that binary operations basically operate with two digits only, and other the technologies that are basically used to build such logics. Uh, it's very introductory here. I mean, it just gives you here what it's saying that we have a threshold value for 0 and 1. So Basically, if we have something near 5 volts, we call it 1. Whatever is close to 0 volts, we say is 0. So this is that if we are basically it's high and low is called 0 and 1. So basic operations, Boolean, what we call binary operations or Boolean operations, are basically not and or. These are the very basic operations. And the not operation is basically inversion, where A is the input, Y is the output. The symbol is like a triangle with a small bubble circle in front of uh, it, towards the arrow, which is on the right hand side. So, truth table says that if we apply 1 as the input, the output will be 0. And if we apply 0 as the input, the output y will be 1. So, this is the NOT gate. And gate, if we see the description, the diagram for the circuit diagram for an AND gate, it looks something like a D. It has two leads on the flat side. Uh, These are the input variables, and on in the middle of the curve side, we show the output. Here the output is y. So truth table says that uh, an and if either a or b is zero, like if any of the a or b input is zero, the output y will be zero. Output y is one only when both a and b are one, which is basically depicted by A dot B, or if we write in notation form, or simply AB. The next basic logic gate is an OR gate. OR gate says that the symbol is something like a curved arrow shape with the flat side is also a little bit curved. It has input shown here. It is two inputs, and towards the right hand side, the output is shown by the variable y. The operation of OR gate is that if any of the input variables is 1, your input variables are A and B. So if any of the input variables A and B is 1, the output will be 1. So when A and B both are 0, the output Y is 0. But if any of the inputs, uh, your A and B, so your B is 1, so the output will be 1. Here only A is 1, B is 0, yet the output will be 1. Yeah, and in the the fourth case, uh, A is 1, B is 1, so the output is also 1. The notation is a plus sign, a binary plus sign, where A and B are the inputs. So uh, these operations are negated operations and an exclusive operation, exclusive OR. Basically, NAND and NOR gates are called as the universal gates, and, and I'll try to just touch this fact on the universal gates concept later on. A NAND gate is simply the symbol is simply the AND gate, but a bubble on the left side, on the right side, just as we had it in the AND gate. So as in AND gate, we had a circle towards the right hand side, towards the output side. In NAND gate, the diagram is very much similar to the AND gate, but with a bubble on the towards the output side. What NAND gate says that it is exactly the opposite of an AND gate. So it basically stands for negated AND. If we remember in AND gate, when both A and B are 1, then only the output is 1. And in all other cases, the output was 0. But in NAND case, the output is exactly the reverse of the AND gate. So, for example, if we take the inputs are 0 and 0, the output will be 1 because when we add, the output of A and B operation will be 0, and we have to negate that operation, that output, to get the output of NAND gate. So that's why it is 1. So similar case, we see like when inputs are 0 and 1, the output is 1. When the input is 1 0, the output is 1. But when both A and B are input as 1, we can see the output goes as 0. Uh, as in negation, it is the notation is simple A dot B, and the whole is uh, subscribed under a bar. So you write A dot B and write a bar over the top of it to get the notation of a NAND gate. Similar is the case with NOR gate, where in OR the uh, 0 0 inputs gave a 0 output, and all other inputs gave a 1 as the output. NOR gate is just the negation of OR gate output. And so when the inputs are 0 0, the output will be 1. And in all other cases, 0 1 1 0 and 1 1, the output comes out as 0. The notation for the NOR gate is A plus B, the whole bar. Uh, XOR is a very special case where the output. Uh, okay, so let us see the diagram, the circuit notation for an XOR. It is an OR gate is the symbol of the OR gate, but a curved line is parallel to the input side of the OR gate. So uh, it happens like how does it operate? XOR stands for exclusive OR, and the output will be 1 when exactly one of the input is 1. If both the inputs are 0 or 1, then the output comes out to be 0. And and XOR is denoted by A, and the operator here is a plus sign with within a circle, such that the ends of the plus sign uh, touch touch the circumference of the circle. So this is the sign of an XOR A XOR B. A XOR B can be easily calculated also as A B bar plus A bar B. Uh, these are the basic logic operations and basic rules. So an AND operation is commutative. So basic what it says that also this is true for an OR operation. So if A and B uh, are ANDed, so A AND operation with B is the output will be same as B uh, AND operation with A input. So this is commutative. And AND operation is associative. So basically, it does not matter in what order you perform the AND operation in a long change of AND operations. So if we perform the AND operation on A and B here, and then AND the output with C, the result that we get is similar or is exactly equal to what we would get if we uh, perform the B and C operation first, and perform the add operation to this product of B or C. So the sequence in which we operate is not uh, does not matter. It does not change the outcome. This a similar rules apply for OR operation also. Here it says what Boolean says that negation of a negation. So A, when we negate it twice, we again get back the A. So the negation of 1 is 0 and 0 is 1. So I think we have a truth table here which explains that say that A is 0, then A bar will be 1. Now A bar is 1, that is not of A. Then if we again apply the not operation on this not A or A bar, we will come back to the original input that was 0. Similar is the cal like the logic for A as 1. So uh, uh, if we negate it twice, the answer will also be same. There are some other theorems also. Basically, we have to consider if A is added with a 0, we will always get or is ORed with a 0. When we perform an OR operation of any input with 0, we will get the original input. If we OR anything with 1, we will always get a 1. And A ORed with itself will always be itself. Like if A is 0, then 0 or 0 will give you 0. And if A is 1, then 1 or 1 will give you 1. And again, an interesting thing here, A, when we OR it with its own negation, so A ORed with A bar will always give you 1. Uh, the next four theorems are basically for uh, OR operations. So any input when we, is for AND operation. So if any input, if we add with the 1, we will again get the original input. So 0 and with 1 will give you 0, and 1 and with 1 will give you 1. So it is the basically same input we get every same output is the output is the same as what we had input. Any input if we or with 0, it will give us 0. It is very evident from the initial definition that we had made. And an input when it is AND with itself will again give you A, the same input. So if 0 dot 0 will give you 0 and 1 dot 1 will give you 1. And any number when we AND with its negation, so A AND with A bar will give you 0. So if we draw a truth table, it will be like uh, for A is 0, A bar will be 1. So 0 multiplied by 1 or 0 and with 1 will give you 0. And if we take A as 1, so A bar will be 0. So 1 dot 0 will again give you a 0. So these are basically the same theorems that we had. Uh, they are described in a tabular form. Right? So A and B, when A, B, okay. So here, basically what we have to see is that uh, A plus B is always, all right, is it here? A dot B, the whole bar, right? So A, this is when we try to remove the negation, what we can see, I think it's given there, right? This is what I'm trying to say. So A dot B, if we look at the truth table of A dot B, the whole bar, and the A bar or B bar, we can see the outputs are same. So what it says that uh, we can use the similar rule for a longer change also. A distributive loss when we have different operations. How does uh, calculation can be or how these can be expanded is that uh, it's basically distributive. So A when we add with B plus C or B or C, the output will always be A dot B or do it A dot C, A and C. So if we look at the truth table and we take a look at these two rows, the A dot B, B or C, the whole, and AB ORed with AC. If we consider these two columns, we will see that the outputs are exactly the same. Uh, this is like A plus B dot C, right? So this A or with B dot C. So B dot C should we can consider that as in the brackets. So if we open up the brackets, what we get is that A or B and operation with A or C. This can be easily proved by this truth table. If we go back and look at this column, A or BC and A or B ANDed with A or C, these two columns are exactly equal. So I'll just skip to a sum of product form. So there are standard forms of exhibiting or denoting a Boolean equation. So this is the sum of products form. Sum of products, what it says that these could be depicted by so this A dot any basic form of like A, B, C is like the dot operation. We call it as product, and the OR operation is called the sum. So any equation that we depict in this form, like uh, some elements are uh, uh, and operation is performed with some elements like A bar B C bar uh, A bar B C A B bar C bar A B C bar. So these elements are like and operations have performed on basic input elements A, B, C or their negative forms, and these groups are again then ORed with itself by a plus sign. So this sort of depiction of uh, Boolean equation is called as sum of products. So how this is done is uh, we the sum of products says that in this example it gives us that A bar B C bar. So A bar where A should be 0 when it is B, it should be understood that this B should be 1 and C bar, it means that this C should be 0. So this combination is can be seen here where A is 0, B is 1 and C is 0. For this term, the A bar BC, we need the row where A is 0, B is 1 and C is 1. So where do we find this? It is A is 0, B is 1, and C is 1. So the fourth row qualifies for that. So we put a 1 over here under the x2. A, B bar C. It says that A should be 1, B should be 0, and C should be 0. So that is 6, 8. 100 is okay, the fourth one, fifth one. So x3, we put 1 x3 under x3 for this row which satisfies A 0, A is 1, B is 0, and C is 0. A plus the last term is A, B, C bar. So in this case, we need the place where A is 1, B is 1, and C is 0. So A is 1, B is 1, and C is 0. The second last row qualifies for that. So the x4, under x4, we'll put 1 in this 110 row. And all other terms are written as 0. And now we have the final output because they are ORs. So 0, 1, 0, 0, 0. So 1 or 0 or 0 or 0, it gives you 1. So basically, where it is where all elements are 0, the output will be 0. And where at least one element is 1, we get the output as 1. So this is how we uh, get the truth table for it. This form, if you see, this was the product or sum of products form. The next one is product of sums. The difference here is you could see the calculation methodology and the depiction. So here we create groups of summation of uh, basic variables. Uh, so by basic variable, it means variables and or their negations. And such groups are added with other groups. So this is called as the product of sums standard form. If we operate on this again, here what we have to do is we have to select the rows where uh, A, B, C are 1 and we put a 0 over, sorry, A is here it is the inverted operations. So we need to check that A should be 0, B should be 0, and C should be 0 for this term. And we write this, if we consider this as y1, we put a 0 over here. So the next term would be A, B, C bar. So A should be 0 here, B should be 0, and C bar that would be 1. So 0, 0, 1 is 0, 0, 1, the second row. They would depict y2 in the second row as 0. So basically this place should be 0 now in the next operation. So here it happens. Uh, the next one is A bar B, A bar plus B plus C bar. So A should be 1, B is 0, and C is 1. 1, 0, 1. We allocate the column 1, 0, 1, which is this one. Uh, this should be the sixth column. And under Y3, we put a 0 over in the row that uh, is corresponding to 1, 0, 1. And the third, the last element is A bar, B bar, C. So where all the elements are 1, A is 1, B is 1, and C is 1. And we put a 0 on the under Y4, which is this. Uh, as per the definition of AND operation, if any of the element is 0, the output is 0. So wherever we have put a 0, we automatically put a 0 over here in the corresponding Y column. And the others are 1, and that is exactly the same as the previous sum that we had. So I wanted to touch up on these two forms because this will help us to solve the questions where you need to uh, basically convert a given expression from SOP to POS or POS to SOP form. Basic term is that the groups that we had called, uh, if let's talk about this SOP form, standard SOP form, the groups that we had formed here, okay, the numerical equivalent of them is called a minter. So, as we have depicted this in the standard form, so A, B, C bar is a minter, A bar B, C is a minter, and A bar B, C bar. This is a minter. So here, for this function x, we have three minters. Uh, in product of sum, we call these groups A or B or C. Uh, the second group is A bar B, C, A bar or B or C. And the third group is A bar or B bar or C. So each of these group is called as a max term. In Boolean algebra, we need to also consider uh, don't care conditions. They make designing circuits for digital logic quite easier. So X term is like we can ignore it or we don't care whatever it is. So if our in our reduction, if you find that a zero or a one helps in place of a don't care, we can consider that as the input and we can design our digital logic without considering it as without affecting the total logic, output logic in our programming, in our digital logic programming. So this is the last slide. Uh, I think we can uh, go with the um, sums. If you,
Sure. Should I share my screen?
yeah,
Yeah. Is the screen visible?
yeah,
Okay.
we can see a stream.
Okay. Yeah. Okay. Okay. So hello everyone. I'll be giving a brief introduction about differentiation. So first of all, what is differentiation? So differentiation is the method of finding the derivative of a function. So this is basically a process where we find the instantaneous rate of change in function based on one of its variables. Now, where is this particularly used? This is used in back propagation in machine learning. Right, so that is a very most common example, I would say. So yeah, so it's basically represented in the form where the derivative of the function is dy by dx, where y is the f of x of any function. So yeah, so here this talks about that it can be defined as a derivative of a function with respect to an independent variable. Now, what this independent variable will mean, so it can be, let's say, if I'm giving an example of 2x square, so x will be the independent variable. So derivative of 2x square will be, derivative of x square will be 2x. So now let's say that y is equal to f of x can be a function of x. Then the rate of change of y per unit change in x is given by dy by dx. So this is also called as the slope. If the function goes a particular change of h, then the derivative can be defined as f of x plus h minus f of x upon h. Now this is a more complex method than the initial one, but still it is pretty valid. So I'll just go through it. So here, this is the formula. So let's say that we want to find the derivative of f of x equal to 2x. So here we have f of x, right? So in the place of x, we will substitute 3 first. So it will be f of 3 plus h uh, minus f of 3 upon h. Then here it is that our function is 2x. So 2 into this part. So after multiplying by 2, we will get this. So this is 6 plus 2h minus 6 by h. So 6 and 6 will get cancelled. It will be 2h by h, where the derivative will be 2. So these are the particular notations where dy dx is called the Euler's notation. The small dy by dx is called as the Leibniz notation, and f dash of x is the Lagrange's notation. Now here it talks about two functions, linear and non-linear. So a linear function is a function that varies at a constant rate. So overall, the rate of change of the particular function will be same as the rate of change of function at any point. So it won't change at any point. Meanwhile, for non-linear, it may differ as a, right, as the nature of variation is based on the nature of function. These are the differentiation formulas. I'll go through them later. Right, so these are the particular differentiation rules. So we have 4 rules here. First is sum and difference. So in this particular, what this particular rule says is that we have a function f of x, and let's say this function is the addition or the subtraction of two other functions u and v. So when we take the derivative here, this will still be the derivative of the individual functions u and v. Now coming to the product rule, we can see that it is not same as the above. So taking a function as f of x, this is the product of u and v. After doing the derivative, what we will get is we will get the derivative of u into the function v, and the function u into the derivative of function of v. Now what the quotient rule says is that, let's say we have a function, and this function is uh, u function divided by v function. Then I can say that it is the derivative of u into vx minus ux into derivative of v. So we can see that this is as same as the above, only the sign has changed here, and this is subtracted by v of x square. Now here comes the chain rule. So what this chain rule says is that, let's say if we have a derivative where it's dy by dx, so this can also be written by two separate functions where it can be dy by du into du by dx. So here are some real life applications. So acceleration, that it can be the rate of change of velocity with respect to time. And of course, I told that it is used in back propagation as well to find the gradient of the function in machine learning. Gradient descent is actually an optimization algorithm where this is used. So let's proceed to the question. So here it's written that differentiate this particular function where it's 6x cubed minus 9x plus 4. Right. So now I'll go to the formulas. So here we'll be using this particular formula, the sixth one, where it says that if you have a function and if it is x raised to n, so this will be n into x raised to n minus 1. So now we will use this formula here. So we have 6x cubed here. So this will be 3 into 6 into x raised to 3 minus 1. So this will be 2 divided by 9 into x. Here the x is gone, as x is 1, then 1 into 1 minus 1 is 0. That's why we have only 9. And meanwhile, the derivative of a constant is 0. So it's 18x square minus 9. Differentiating this particular equation, we see that dx is outside in the brackets, then we'll first what we'll do is we'll multiply here, so it will be 3x cubed minus 9x, and this will be 3 into 3x 3 minus, raised to 3 minus 1, which will be 2, so 9x square minus 9, and this is the final answer. Yeah, so this is pretty much it for the first part. Should I also go with the next one?
If you can go ahead. Sure,
Okay.
go ahead.
Yeah. So here comes. So this is the differentiation questions. So here we have different formulas where to say that if x raised to n, then n into x raised to n minus 1, which we saw in the previous. Then it's e raised to x function, e raised to x derivative with e raised to x. Yeah, so we will be using these ahead. So yeah, so this is the first question, where it's x raised to 5 with respect to x. So if we have y which equal to x raised to 5, then I can say that it is 5 into x raised to 5 minus 1, which is 4. So it's 5x4. Differentiating this, so this is again the same. Okay, so this is again the same, where actually the sign of the power does not matter, because again, just like the formula, what I have to do is I have to multiply this minus 4 here by 20, and then do minus 4 minus 1, which will be minus 5. Now differentiating the, I think this is called as the log, if I'm not wrong. But yeah, so
Yes, log, it is log.
yeah, so log of 10 here is, so the derivative of this is still 0, as this is a constant. These are the different rules that we saw before. Okay, and here, yeah, and this is this the sign. This is the question where it's saying differentiate sine of 3x plus 5. So here in the formulas we have the formula of sine. So they say that sine, so the derivative of a function, like derivative of sine x, is cos x. Right, so now here we have sine of 3x plus 5. So we will use the chain rule here. So what is the chain rule? So this is the chain rule where dy of this particular thing will be equal to dy by du into du by dx. So this will be sine 3x plus 5. We will take the derivative of this thing first, then we will multiply it by the sine of whatever is in the bracket. So this is 3x plus 5. So then we will take derivative of this thing. So this will give us 3. So this will be 3 cos 3x plus 5. Then differentiating the tan square x. So differentiation of tan square x will be first to take the derivative of this thing. So this will be 2 tan raised to 2 minus 1. This will be 2 tan x. And derivative of tan x, as we can see here, is sec square x. So yeah, and then we have again sine square x. So what we'll do is we'll first take the derivative of this thing individually. This is 2 into sine x, so we have 2 sine x, and taking the derivative of sine x will give us cos x. Yes, so I think I'm done with differentiation. This is also another part. Yeah, I think this is the same thing. Should I go through this? Hello.
Sorry. Are you ready, or do you want to do it next? Let's do it next. I think we'll have to do some examples, right?
Uh, okay, so here there were some basic questions that gave an idea about
Mhm.
it.
Yeah.
Yeah, so these were where the questions were. So I did go through them.
Yeah, yeah, I saw that. But do you want to continue on that? If you want to continue, go ahead. Another 2 minutes is there. Sure. No problem.
Yeah, I think I'll just go through this if
Yeah,
it's
just go through.
possible.
The sum rule of differentiation.
Okay, okay. So okay, again, this is based on formula only.
Mhm.
Yeah, okay. So I think yeah, then yeah, okay. I think this should also be easy to forget.
Correct.
So should I go ahead or
Yeah,
we
yeah.
have
Go
to?
ahead. Go ahead. Go ahead. Just finish. We'll take this further. After that, we'll go through the problems next time. Yeah,
Okay.
the exam
So
problem. Yeah.
okay, yeah. So this is the power rule of differentiation. So they say that it is one of the most common rules of derivatives, where the x is the variable and is raised to the power of n. So this is again the common formula that we also saw before.
Correct.
So here the example. Okay, so this is okay. We know this. Then coming to the sum rule of differentiation. So what this rule says is that if the function is sum or difference of two functions, then the derivative of the function is the sum or difference of the individual functions. So this also we did
Correct.
see before as here as the sum and difference. So
Correct.
we can take the derivative of these things individually. So x derivative is 1 and x cube derivative is 3x squared. So this is pretty easy. Then we have the function of 6x squared. So this again will be calculated by taking the derivatives of the individual variables here.
So it will be 2 into
Yeah,
2 into 6, 12. That is 12x minus 4. Correct. That's the correct answer. Go to the end answer. Yeah, 12x minus 4 is the answer. Next one.
yeah. So this is the product rule of differentiation. So what they say is that if we have uh, a function where the function is product of two different functions, then it will be the derivative of one function multiplied by the other. So here one function is u of x, so it will be the derivative of u of x multiplied by v of x, then derivative of v of x multiplied by u of x.
Correct.
So taking the case of here, so what we'll do is first we'll take the derivative of x square, which will be 2x. So it will be 2x into x plus 3, as we can see here.
Mhm.
And then what we'll do is we'll take the derivative of this thing, which is think this will be 1. This
1.
will
Yeah.
be 1 into x square.
So, correct.
Yeah, so 1 into x square, and then this will be 2x square plus x plus x square, so it's 3x square plus x.
So, yeah, good. That's good. Quotient
Yeah,
rule.
yeah. So the quotient rule says, so the quotient rules, I would say numerator is similar to the product rule. The only difference we have is of the sign,
Mhm.
and this is and the denominator is v of x of square. So here we can see that it is, the question is that it's x plus 2, the whole cube divided by the root of x.
Mhm.
So root of x we know is x raised to half,
Mhm.
and x plus 2 cube will be x plus 2 into this thing. So this will be x plus 2 into x plus 2 square. So I think here they have just use the a square plus 2ab plus b square formula.
Correct. Correct.
Then okay, so this is again multiplying it by x plus 2 gives us this. Then they have took this ahead, so then they had made this into the product rule, it seems.
Mhm.
Okay, no, they are just simply multiplying it, and
Mhm.
after multiplying they got this.
Mhm.
Now they differentiated the individual equations. So this is 5 by 2 into x raised to 5 by 2 minus 1. So this will be 5
2 by
minus
2.
2 by 2, which would be 3 by 2. Yeah.
Mhm.
Yeah, and doing the same for others will give us 9. Yeah, so here also 3 by 2, so 3 by 2 into, yeah, so this will be 9x raised to half, and then we have 6 into x raised to half, so this will be, so here we have 12 into this, so it will be 6x raised to half minus 1 third second minus half.
Mhm.
Yeah, and then we have this thing, so this is minus half into a, so this will be minus 4 into x raised to minus 3 by 2. Yeah, then the chain rule of differentiation. So how this works is we have this example of that this function is x raised to 4 minus 1 raised to 50. So what they did is they took this function and they called it f of x. Then they called g of x as x raised to 4 minus 1 and n raised to 50. Okay, let me have a look at the formula. Okay, so the formula says is this. Okay. Then what they've done is, okay, then they have x raised to 4 minus 1, and then they have told that f of x is equal to u of g of x. So, okay, I think this is mentioned here. I think yeah. Okay, so yeah. Okay, so this is the LHS part, I think.
Mhm.
So okay, so what they have done is they have, okay, so they told that this function f is u function. So u function is t raised to 50 into the g function, which we have called as x raised to 4 minus 1. Then they have applied chain rule here.
Mhm.
So applying this, they got t raised to 50. So t raised to 50 is this. So this is of course 50 raised to 50 into t raised to 49, and then they have calculated this individual. So they are applying the chain rule here, where du by dt is this part and dt by dx is uh, the derivative of this part. This will be 4x cube, I guess. Yeah. So then it will be the 50x 4 minus 1 raised to 49 into 4x cube. This is this. Okay, so multiplying this will give us this part. I think they have done is, think 4 into 50 is done here, then they have just took the variables and gave us this.
They have taken df by dx of 50 e raised to 9 to 4 is cube. So they have actually divided it into x raised to minus 1, which is they substituted, right? T is equal to t equal to what is t equal to?
Okay, no, so t is not equal to anything. T is, okay, so t equal to this
Is
part.
4 is
T
to
is
4
g of
minus.
x. T
Yeah,
is the u function.
correct.
Okay, yeah, yeah. So
They
t is the u
substituted
function. Yeah.
x raised to 4 minus 1, they have substituted there. Yeah.
Okay.
That's why. Where did x disappear? I was trying to say. Where did t disappear? So they have x minus. They have taken x raised to 4 minus 1 and substituted it and got it. That's perfect. That's perfect.
Yeah. Okay. Then in this exam. Okay, I think we can have a look at this as well. So c raised to sine of 2x.
Mhm.
So here we have, so here they have said that this f function f at this part, and then g of x will be, I think, sine 2x.
Mhm.
Okay, yeah. Then they have done chain rule. So then they'll calculate this individually and this individually. So du will be uh, okay. Okay, so this is g of x is sine 2x, and ut is e raised to t. Where is e raised to t? Okay, okay. So sine 2x is t here, and sine 2x is t, and that is e raised to t.
Correct.
Okay, so then they then the chain rule. So doing it gave
D by dt of e
d
raised.
by dt into, okay. So this
E
is
raised to t is always e raised to t. So left it as is.
yeah, and then they have done is d by dx into sine 2x. So this will be, I think, derivative of 2 sine 2x into,
2 sine 2 cos 2x, right?
oh,
Yes.
okay, okay, they, okay, okay, yeah, okay, this is,
Sin x
okay, yeah,
is
they
sin of
took derivative of 2x individually, so this that will be 2, and
2.
then sine 2x is cos 2x. Okay,
Correct.
perfect. Yeah, okay, then they took this, so
Yeah.
then they substituted it
Sin
here.
Sine 2 raised. Yeah, correct.
Yeah, so this is e raised to sine 2x into 2 cos 2x. It's okay. So this is the simple multiplication, I guess,
Mhm.
and it gave this.
Yeah, just they would reverse that. That's it. Fantastic.
Yeah, I think we are done with differentiation, sir.
That's good. So, Jaymeet and Nikhil, anything you want to add? How was it? How was it the first two part? Went well, right? Did Yes follow everything correctly? What happened? What Jaymeet did? Yes, I'm asking you.
Yeah,
How did it go? Jaymeet, you followed first.
yeah. First it was started by Jaymeet, and then
Nikhil.
Nikhil said,
Huh.
and then me.
So digital electronics you followed, right? Well, whatever Nikhil did.
Yeah, I mean, I was paying attention,
Okay, good.
but I don't think I have that in DA.
Yeah, okay. So you'll have to do a little more to check it out because DA, whether digital design do you have? I don't know. But if you understand the gates, that is good. So Jamie, any comments from you?
No, sir, nothing.
Everything is fine. Okay, so we'll stop
Yeah.
recording and then I will just a second. Let me stop recording. We'll go into the questions next week, but whatever we have covered, we can extend that further. Something on the integration and something on the in the digital. Nikhil, what do you want to add next week? Any idea?
So next week, this week we had only the theoretical things.
Okay,
Next week I will be taking the practical, I mean the numericals
very good.
and gate questions.
Yeah, I think it was a good session, excellent session. I can see you people have exactly contributed whatever. So same way you plan for next week, what do you want to contribute? And then we can make sure that each one contributes and learns from each other. At the end of the day, it is learning, right?
Yes.
Was able to solve the problem. I think differentiation was at least I dropped out sometime and I came back during differentiation. So I felt good that Yash is able to manage well. So we have a good group now. Everybody can learn something and share something. So it will be triple in 1.5 hours. Actually, it will be we'll be learning around 3 hours of things. And then when we go back on our own individually, we'll be able to score. So basically, the ability of the collaboration is that you will be able to get at least double the output you would normally do. And plus, since this is a session which is like it becomes habit that you are always doing something. So by the time you learn. So I hope this has helped, and we'll meet next week for the same thing. And also Wednesday we'll have that risk five. And Monday, Wednesday, Friday, as usual, Jaymeet. Jaymeet is going to continue on the kernels because kernel has got multiple in the SVR. And that is, SVR is a, what do you call, uh,
SVM
sup-
support vector machine
support vector SV
machines
mechanics, right? Support vector mechanics mechanism.
machines.
Machines, yeah. So SVM we did without the kernel tweaking. We did one RSB, I think, and they
Uh,
called it. So
Actually, I tried using the grid search for all three, but the thing was that in Jupyter it was not running for some reason. So that's why I had to do it only on one kernel.
that's okay. So
Yeah.
what I will say is take a look at the YouTube
Yeah.
presentation of others and prepare for Monday, and that's all. So
Yeah.
we are done for this week. Hopefully you can have a peaceful day tomorrow, and then Monday onwards again our journey starts.
Yeah.
So we'll continue on that. And thanks, Nikhil, for handling the whole, because at the end somebody has to uh, moderate it, and so I think it was excellent. And I'll post it once I'll also watch and post it tonight. Okay. And so